the paper that I have been spending a bit of time in the past couple of days is Nova. This is not useless. Can't just use this. Gosh. Here you go, Nova. And there was a swap in the order because it kind of makes sense for Nova to go first, and then there's precursor to Supernova, which also precursor to Protostar. So I'm going first. And it won't be like super math heavy. Most of the math are very simple. But what I would like to talk about is how the paper is being structured, and from step by step, how do we see from R1CS to the construction of Nova. So I'm someone who hates spoilers. So I would just, before I start, I would just like to map out how the paper goes, and then I will walk through each step. So the first part of paper talks about R1CS. And and there was explanation of how an attempt on R1CS is used for folding schemes, and it didn't work out well, and therefore there was introduction to a second part of the paper, relaxed R1CS. And over here we'll walk through some of the tricks and tips as to how you're able to then slightly kind of say add a bit of additional variables and constraints, so-called, to the R1CS so that you're able to unfold it. And moving on, we will then introduce this thing called the committed R1CS, committed relaxed R1CS, and we'll see why it's being called committed later. But the key idea is that the witnesses and the error terms that also relies on the witnesses are being shown to the verifier, which you do not want that. You kind of want to commit that. Number one, to make it smaller. Number two, also to kind of provide some sort of hiding as to what the witness really are. What else? This is where I don't remember stuff now. If you bear with me. And wait, one sec. Construction, and then we will talk about a non-interactive version of the committed relax. I can't spell. CS, and non-interactive is very important. You see why, because there's some parts of the Nova construction that requires you to have the non-interactive. There's no way for you to request an oracle from the verifier, and therefore you need a way to convert it to non-interactive. And from here, we'll then move on to the IVS construction, and this is where the most of the introduction to the Nova part will come in, and then we'll see how do we use SNARKs to further reduce the precise and also the verification time of IVS. And finally, this is a part that I would omit. The paper specifically chose a Spartan as the ZK SNARK proving system to IVS. And this is where we are not going to talk about this today, mainly because number one, Spartan is something that I do not understand. Number two, it's towards the end and I don't understand the math. So okay, cool. So far so good. So this is how we are going to look like. How my presentation demo is going to look like today. Sorry, what? 5? IVC. Sorry. Yep. Thank you. IVC, incremental verifiable computation. So step 1. R1CS. This is going to be a repeat of what Dr. Gore mentioned a couple of days ago. So but I will still go through it for the benefit of others. So we define a relationship between a couple of matrices. A couple of matrices where Z it's going to be a vector that's made up of an x. I would define what x is later. W and a 1. I have no idea what the 1 is. It's there for a reason. I have no idea why. Probably have to read up RNCS paper to understand why. So X is what we call a public instance. It consists of the public inputs and outputs, because outputs has to be public. So it's made up S. W is a witness, the so-called private input, and 1. So these made up the Z variable, and A, B, and C. Basically, you can just think of A, B, and C as the representation of the circuit. So we have the circuit. At the end of the day, it is converted to this A, B, and C matrices of M of N, or I can't remember the exact size, M of M or something. Can't remember. But ABC is just our program. That means it won't change throughout the entire explanation of today's demo. And the problem. So then we define how do you want to. So the goal of this paper is to try to fold it. So that means you're trying to combine multiple instances of this circuit, of the same circuit, into one circuit, one instances. So imagine that now we have AZ1, BZ1, CZ1, and you have AZ2, BZ2, CZ2, and notice that the ABCs are the same. What I'm changing is I'm only changing the Z so that it will be Z1s and Z2s, meaning they mean different things. And obviously, naturally, this one is also X1, X2, W1, W2, and this is 1, obviously. So the goal of this is to somehow merge them into a resultant RNCS somehow. So at the end of the day, we do not have to check the proof twice. We only check it once for the resultant RNCS. So obviously, we have seen that this is something that we won't be doing, and the reason why is because when you try to merge it. Okay, so when you try to merge it, we perform this thing called a linear combination of this thing. So you can think of X as a linear combination of R X1, and this is a very common technique to sort of like combine multiple equations into one equation. And this R, it's what we call randomness. It comes from the verifier. I forgot. Okay, wrong spelling. And so with the aid of a verifier that will give us an oracle, access to a random oracle, we are then able to combine these two, and we have also the trust of the verifier, because this R is given by the verifier, and therefore he or she is able to trust that this is done correctly because R is by him, and there's no foul play when we are merging these two equations. And I can go on to then represent similar instances for at the end of the day. What we want is that we want Z to the resultant of Z to be something like this. So this is what we want to achieve at the end of the day, right? I'm moving over to the other side. So how do we fold it? A very naive technique is that we just do this plus RZ2 plus B. Sorry, that's not plus. It's this matrix operation. Z1, 2, C, Z1, RZ2. And if you were to open up the entire, try to do the multiplication and so on and so forth, what you would get is something like this guy. It's going to be a whole mess of So blah blah blah. The point is there's a whole bunch of this thing what is called the cross terms that wouldn't allow us to satisfy CZ1, which is which is going to be plus RCZ2. So because of this, the existence of cross term, okay, we can kind of see that this is CZ1, right? Which is this part. But then we will somehow need RAZ2, RB and BZ2. But because of the existing of this combination of so-called mesh, we are not able to properly fold it. So, which is why the R1CS, folding R1CS naively does not work. And also, another intuition is also when we try to fold the Z's, this is so hard to write. 2, it actually, if we were to do this naively, we would actually get something like Z2 W2 and 1 plus R. Yes, and this is not exactly in the form that we want. So because of the existing of cross terms, and because even on this step alone, we are not able to fold our Z instances, we are not able to use R1CS naively. So that's why the introduction of this thing called a relaxed R1CS come into play. Is it okay for me to read? Okay, just 1 second for photo, 2 seconds for photo, 3 seconds for, okay, cool. I'm just gonna erase all this mess away. So, and hence, okay, I still got that, that's good. Relax R1CS, which kind of define R1CS in a separate, something that we're not used to. So let me define R1CS here. This is our good old R1CS that we know and love for, using Graph 16, so on and so forth. So the React R1CS will look like something like this. Z is the same, but this part is different. So notice that what I have added is I added a U and an E. This is sort of like a trick or a hack, I would call it. The E basically would represent all the cross terms. That's E. And U, what's U? U will then absorb, I think the R here, and some of the terms that are being introduced when we are performing this folding on the R1CS previously. So at the end of the day, after some mess here, which I'm not gonna replicate, what you can see, it's if we were to naively apply, not naively apply, but to then reapply our linear combinations of our Z's, you see, you see, square bracket, so that I don't make myself. Okay, there we go. And if I were to expand it and shift things around, I would end up to have something like, okay, wait 1 sec first. So it was something like this, R square U2 C2 U2 C Z2 plus RU1 CZ2 plus RU2 CZ1 plus a bunch of mess that we have introduced, which I'm not going to write down, so I'm going to write E because I know that's going to be part of E. And this part can be conveniently factored out to be something like this. So if you do not believe me, you can do this on your own and you get this one, if you do not believe me. And this guy looks awfully familiar with this, right? And this guy looks very something that we know of with this, and therefore we got this one. So what I'm trying to say is that with the introduction of U and E, we are able to then sort of absorb, I don't know if this is the right term, to absorb the weird cross terms and the weird behavior, and then represent it nicely into this relationship to also end up with the same relaxed RNCS form. And this is very key. This is key to folding, because when we fold, we want to make sure that this form is maintained, because imagine if you have a lot of cross terms like this one, it will expand, it will grow with each fold, and at the end of the day, it will just become unbearable. Maybe you can fold it once or twice, but you definitely don't want to fold 5 times because you have like so much cross terms, it'll be such a mess. But with the introduction of E, you can see that this is so elegant. It's always the form will always get maintained after each cycle of folding. Okay, so so that's this. So again, I am going to define how this looks like. Oh, C Z. Oh shit, ran out of room. We don't need this anymore. We don't need this anymore. We also do not need this anymore. Plus A. Oh, actually, we can't need that. But notice that Z that we use a lot in this so-called folding. So let me remind you how Z looks like. Z is actually what's this? X, W, and now it's going to be U. Yeah, there you go, U. Thank you. X is public, so we are okay to show it to the world. U, it's also okay to show it to the world because it's public too. We don't really care. W, however, is something that we do not want to reveal to the world. It's private. And E is made up of a bunch of cross terms that uses Z as well, right? So what we want to do next is that we want to commit W. So using whatever hash functions that you want to commit W to form this W bar and E bar, so that we are able to then not reveal W. So by having this hiding property of a hash function, we are able to so-called not reveal W to the world, which is very crucial to our later steps. So this is why we commit. I'm going to have it over here. We commit, so introduction of W bar and E bar. Cool. And obviously, the hash function that we use will need to be homomorphically additive, because this W that we have over here, we also need to satisfy our good old folding, how can I say, relationship that we have seen a couple of times already. Same goes to E. So should the hash of E1 plus and random function plus bar E2 bar be fold together, it should have a resultant E bar, because, and this only works only if the hash function that you use to commit W it's homomorphically additive, which is something that we will need in folding. All right, cool. So at the end of the day, what the verifier will need, let's see, let me remind myself what the verifier will need. Oh, is these two, plus, of course, we need to know this one. So, and of course, we have the x's. I'm very disappointed in my own writing. Okay, so these are what the verifier can do on their own. So they can verify that for each folding, these are consistent because they are able to have access to this one, this one, this one, this one, obviously for these two as well. And then they are able to reconstruct this on their own. On the proving side, we definitely need a bit more. We will need E as well, because understand that E is something that we can't share to the verifier, but the prover can obviously have access to. And we have W. Actually, I kind of like have ignored the R's, the linear combination of R's that used to fold for E and W has to be different according to the paper, and they have to be folded via a relationship as well. But for simplicity, I'm going to ignore them. So a huge caveat here. So yeah, understand that at the end of the day, the verifier is able to verify the relationship after folding using this relationship, and the prover will fold using this relationship plus some R foldings, which I'm not going to go into because I forgot. So now I'm too late to go back now. Yes, there you go. And this is something that we'll need later, especially when we look into IVC.
Sorry.
Yes.
So there's a problem here.
Oh shit.
E equals to E1 plus.
Oh, sorry. I made a mistake. Yes, thank you for the reminder. Okay, thank you. That is a mistake indeed. Even here is a mistake. So it looks like this. T. What is T? You may ask. T is the cross terms. They have defined this bunch of kind of like a half cross term thing. So it's a bunch of equations. So I'm going to write as T. If you do not know what T is, do not worry, because they merely represent the A's, C's, Z's, and somehow they have a weird relationship to do this. And of course, this one has to be very similar to this one, and this is not correct as well, obviously. And I need to also have a commitment to T. Let me just add it here. But T is going to be the same all the time, so you don't have to fold T. Am I right? No, I'm not. we need to fold T. We need to fold T. But it's a huge bunch of AZs, Z1, Z2s, and blah blah blah. Yeah, and then you can get T once you commit it. So probably T bar here. And I'm not gonna write it down, but you get what I mean. Yes. So this is how we are able to perform some magic on the committed witness and also the error terms, the error cross terms, the cross error terms. And okay, the takeaway of that is that, oh yeah, this is a takeaway. And of course, T bar if you take away. Cool. I'm going to erase this. And this. So non-interactive VT is something that we take a lot for granted, and we often use Fiat-Shamir transformation. There are some arguments saying that Fiat-Shamir transformation may not be secure or not, but we don't care. For now, we are just still going to use Fiat-Shamir transformation. So non-interactivity, committed, relax, R1CS. So the key takeaway of how do you, so the goal is to generate random oracle R without involving, I can't spell nowadays, involving verifier for each round of folding. So recall that we see the R's appearing here and there, and those R's actually come from the verifier. So to make it non-interactive, there needs to be a new way for us to generate the R in such that the verifier will also believe that R is generated correctly. And Fiat-Shamir transformation is a very common technique that is used to perform that. And this involves this relies on the presence of hash functions, because hash functions, the good ones at least, are believed to be uniformly distributed. That means the randomness are something that you cannot predict, and It's very nicely even. There's no bias and so on and so forth. So therefore, a good fetch image transformation will rely on a reliable hash function. And the end goal of this is obviously to get R. So so normally in normal ZKPs, field transformation will take in all public inputs, and then pass it in onto hash function, and the resultant result will then be the randomness. And the same it can be said here. Let me say it over here. It's using the same similar technique, but I need to find that equation. Yeah, there you go. So R now is being generated as the input of our U1, U2. As to why these are selected, I do not know. VK is our verification key, which is also public. We don't have to care. And T-bar. T-bar is the committed, if you recall, T-bar is the committed value of our somehow partial. It's not exactly cross term, but it has some cross terms in there. So I will just call it partial cross terms for now. T-bar? Oh yeah, hash function. Oh. Okay, one thing I hate about Nova paper is that the notations are like the worst ever, right? Hash. I think this is better. Why can't you just type this out, right? How hard is it? So yeah, there you go. So the takeaway of this part is basically hash of U1, U2, VK T bar to get the randomness. To get randomness. Okay. Cool. So up till now, we have not actually gone through the IVC folding method. What we have seen is that we have seen a technique to fold relaxed RNCS, to fold computation or circuits via using the relaxed RNCS form, the committed relaxed RNCS form in a non-interactive way. So this is what we have seen so far. And moving on, there's this IVC thing. So a quick recap of how IVC looks like is that it has one function. Maybe I give it f because everyone loves f's. And let's say you were to perform, you were to have an input of z0, and you have an output of maybe z1. And I would do this, and I would to repeat the f. F doesn't change. What I do is I just use the output as the input of the next round, and so on and so forth. And this can be defined as z n, I guess. The n equals to what? N done multiple rounds, n times, and z0. So this basically means that I'm applying the same function over and over again n times, and this is the final result. So this is what we want in IVC, and we want to be able to fold. We do not want to have one RNCS for each round. We want to combine the RNCS to form only be able to represent this in one single relaxed RNCS per se. Obviously we can do it per round, but what's the point of having to do a round when we're talking about folding today, right? And of course there are many benefits, not just because I'm talking folding today. So yeah, there you go. So this is what we want to achieve at the end of the day. So this part is a bit tricky. It took me a while to sort of get it. So they kind of like introduced this thing called the augmented f. They call it f prime. So f prime, it's a stronger version of f in such that it also includes the includes folding of proof from previous rounds. So this part, they have nicely drawn a diagram, which I'm going to redraw for everyone's convenience. So understand that f is a function that is used in IVC. They introduce also an additional layer or logic per se that allows you then prove that each f is being folded in a correct way. And this is then represented by f prime, because now f prime consists of more functions and more logics and more features per se, to our good old f. So you also have this one. So this is the introduction of f prime. There you go. So how it looks like is that IVC. Hang on a minute. Let me try to recall. So they then introduced two terms that that would be useful. So they introduced another u. Okay, notice that I'm using a different symbol now, and u will mean that this round is being proven correctly. Ui means that round I is proof. Of folding. I made the entire thing up, but but what I'm trying to say is that UI is basically to prove that this folding round is correct, and they have a capital U. I means round from round 0 up to I minus 1, the foldings are done correctly. Folding are done correctly. So you can imagine that for the so-called the augmented function, what we want to do for each round is that we want to somehow include this weird u to this big U, so that the next round can have this big U and also include their own weird U. And towards the end, we only need to prove this big U to prove that all the foldings are being done correctly. And this is done using an internal relaxed RNCS, I guess, as well inside IVC. So the diagram illustrates that there are two parts. This is our good OF, which we have seen, and this is the new so-called logic, proof of folding logic, POF. POF. There you go. So what POF takes, it takes weird UI, which again is the proof of folding for this round, and big UI, which is the folding up to this round. That means before this round. So they need to somehow combine these two to form UI plus 1 somehow. So okay, this is going to be tricky. So so this again. Okay. So this is a proof from a relaxed RNCS. So meaning we have the existence of public instance, witness, and the other U as well. So what they're going to do is that for each round they are going to check. Okay, it's a bit too quick. So there's a round that combines U1 into big U to form UI plus 1. This is this round. Okay, this round you see. This is first step. So this is the verification, the verification step, which I'm going to do later because you will see why. And this is and after you pass verification, you fold them together. You kind of like combine them to a big U. And after you have a big U, they will actually not just return this. They will actually return the hash of it. Hash of big U. If I understand correctly from the paper, it's because I lost that line, but it's because they sort of want to, they find it hard to kind of like force this in the instance of like u.x, which we'll see later, into running instance u1. I'm not explaining this well. I apologize. But at the end of the day, you have to understand that they are going to hash this thing. Of course, with some other things as well. But the key point is that they are going to hash and return the hash of this big u1. Okay, I have talked about how we force them into a big U, and are returning the hash of big U. Now I'm going to talk about the verification. So before each round, they'll check if the U1 of the public instance, public instance of the proof U1 is the same as that hash. Blah, 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 blah. So inside this little cool little circuit, relaxed RNCS circuit, there is a logic that checks, there's a logic that combines, and there's a logic that outputs. And basically this is the verification part. And of course all the I's, the Z naughts, the Z's will go to F as per usual, and this defines per round of IVC. I do not know if I'm describing this properly, but feel free to ask questions, and if I do not know, we will find out together, or Dr. Go will correct me. But shamelessly asking help. All right, cool. So what we notice now is that if you were to read the introduction paper, at least for me, I realized that, okay, this is what we call IVC proof, right? IVC proof. We are able to prove that this thing is done correctly. But the problem is this is very huge. This is huge. The proof size is, I think, N, ON, and the verification size ON, which is going to be huge. So what they do is that they're going to wrap the IVC proof here. They're going to wrap IVC under a ZK snark, if you want ZK-ness, snark, to sort of bring down the proving time size and verification time. So my mental model will be something like this. My mental model will be, we have an IVC proof from our F0, and we have our outputs an IVC proof. But this is too large. So we wrap that into another snark to have a succinct proof, so to say. So you can imagine that this is going to be like a two-layer kind of proving that is being done under the hood. And that concludes the step 6. And on the paper, as I mentioned before, they go into depth as to how they implement Spartan onto their version of Nova. Spartan is something that I'm not very familiar with, so I'm going to cross that out. But understand that there's a huge part of the paper which I neglect. And there's also a huge part of appendix that talks about proof of why each step is sound, why each step is complete. And those are something that I do not understand. But yes, this is what I have read, at least the most part of it, yesterday night, with the help of Jen, my roommate. So the trick, the hardest part for me in this paper is to understand what on earth is this. Like, I was like, is this a dot product? Is this a product? And then Jen came and said, like, oh, this is X, the object of X. I was like,
yeah, I have that kind of.
Yeah, I was trapped in this thing for 1 hour with a constant oscillation of YouTube and paper. And then I realized what he said. And then we look into the part like, oh, okay, this X is indeed a public instance. So then we conclude that U1 is actually also from a relaxed RNCS, which is like, I think 1 line or half a line. And you kind of have to figure out what on earth is this thing. It's not entirely too clear, but I think once you figure out what on earth is this, everything becomes sort of clear. And then if you keep grinding through, you kind of are able to see how it proves in a way that, yeah. So this is the key, understanding what's the meaning of this symbol. Yeah. So I also conclude that paper writers, such as this guy, is probably not a good textbook writer. So they could have included more words, right? Like, for example, one of those is that little row thing, right? That should, right? So those are the things that I hope they do. So that, so yeah, that's my findings. Any questions? Oh.
Is this the scheme that was in the news some time ago because of a big vulnerability or bug, and that people were able to create proofs of something invalid, something like that?
Oh, that's too vague. There were some vulnerabilities about Fiat itself. There are some vulnerabilities about disproving schemes, But
I
no,
think it was
no.
just a Fiat Shamir. It was a real
Yeah,
bug.
it happened in the implementation because in the paper doesn't use the circle of curves.
What was the issue?
So in the paper does not use circle of curves.
Okay.
And those are two curves that are symmetric.
Okay.
And